Hello friends, myself Rajendra Mahajan presenting my video on Laplace transform of derivative. In this video, I will discuss first statement of that theorem and then some simple problems based on that Laplace transform of derivative. Total 4 problems I am going to discuss. Therefore, watch the video completely for better understanding, clear understanding. Statement is like this. If Laplace of f of t is equal to f bar of s, that is given or we can obtain it, then Laplace transform of d by dt of f of t means Laplace of derivative of f of t is equals to s into f bar of s. What is f bar of s? F bar of s is the Laplace of that given function f of t minus f of 0. F of 0 is the value of the function at t is equals to 0. Similarly, we have second result, Laplace of second order derivative, that is f double dash of t. This is the first one. Then second one, Laplace transform of second order derivative f double dash of t is equal to s square f bar of s minus s f of 0 and minus f dash of 0. And last result, Laplace transform of third order derivative, that is L of f triple dash of t is equals to, for first we have s, for second we have s square, for third we have to start with s cube into f bar of s, then decrease 1 by 1 power, therefore we get s square into f of 0, then minus s f dash of 0 and minus f double dash of 0 and so on. We can increase up to any order of derivative in the same manner. Therefore, once again see all this result. First, Laplace of first order derivative is s f bar of s minus f of 0. Second order, s square f bar of s minus s f of 0 minus f dash of 0. And third, s cube f bar of s minus s square f of 0, like this. Then find Laplace transform of the following. First, d by dt of sin at by t. Second, derivative of t raised to half into e raised to 2t. Third and fourth, like this. Therefore, we go one by one. The first one, Laplace of sin at by t and its derivative. Therefore, first of all, we find Laplace of sin at. We go step by step. It is a upon s square plus a square, a standard result. And we call this as f bar of s, say. Then, by that division by t property or theorem, we get Laplace transform of sin at by t as integral from s to infinity of f bar of s and its integration with respect to s. Then it is integration from s to infinity, and what is f bar of s? It is a upon s square plus a square and its integration with respect to s. A is constant, we take outside the integral sign, and standard result of integration 1 upon x square plus a square, it is tan inverse of x by a. Therefore here it becomes tan inverse of s by a divided by a, limit from s to infinity, a get cancelled, and then for upper limit it becomes tan inverse of infinity and minus tan inverse of s by a for the lower limit. Tan inverse of infinity is pi by 2 minus tan inverse of s by a standard result as cot inverse of s minus a. And we call this as new f bar of s, or f bar of s a new one. Then we go for the last step, Laplace transform of derivative of that sin a t by t. As per that theorem, it is s f bar of s minus f of 0. Therefore, substituting the value of f bar of s, we get s into cot inverse of s by a, s into cot inverse of s by a minus f of 0 means the value of the function. Function is sin a t by t at t is equals to 0. Therefore, if you try to find out the limit by applying indeterminate form technique, we get its limit as a, and therefore it is s cot inverse of s by a minus a as the required answer or the required Laplace transform. Therefore, see the steps carefully. We get the answer as s cos inverse of s by minus a. Then second one, Laplace of d by dt of t raised to half into e raised to 2t. Therefore, we consider f of t as t raised to half. Here power is not an integer, therefore its Laplace is gamma n plus 1 divided by s raised to n plus 1. As per that, it is gamma 1 by 2 plus 1 divided by s raised to 1 by 2 plus 1. Gamma n plus 1 is n gamma n, therefore it is 1 by 2 gamma 1 by 2 and divided by s raised to 3 by 2. Gamma 1 by 2 is root pi, therefore root pi into 1 by 2 and whole divided by s raised to 3 by 2. And we call this as f bar of s c. Then by first shifting theorem, as that term is multiplied by e raised to 2t, we apply the first shifting theorem. Therefore, Laplace of t raised to 1 by 2 into e raised to 2t is equals to f bar of s minus 2, as it is plus 2t, therefore replace s by s minus 2. Therefore, in that previous result, we replace s by s minus 2, so that we get square root of pi by 4 divided by s minus 2 raised to 3 by 2, and we call this as a new f bar of s, say. And then last step, Laplace transform of d by dt of this function, that is t raised to half into e raised to 2t, as first order derivative there, it is s f bar of s minus f of 0. Substituting the previous value of f bar of s, we get its value as s into that square root of pi by 4 divided by s minus 2 whole raised to 3 by 2 and minus f of 0, that is t raised to 1 by 2 into e raised to 2t at t is equals to 0. And therefore, when we substitute t equals to 0 in this term, we get that value as 0. 0 into 1 we get 0, and therefore answer is s into square root of pi by 4 whole divided by s minus 2 raised to 3 by 2 as the Laplace of that derivative term. Our required answer. This is the second example. Therefore, go through all the steps once again carefully. Then the third example, very simple example, Laplace of d by dt of cos t. Here it is not expected that we have to differentiate cos t and then Laplace. We have to apply this theorem. Therefore, we first find the Laplace of cos t, standard result, as s upon s square plus 1. And we call this as f bar of s, say. Then applying that theorem, therefore Laplace of d by dt of cos t, as per that theorem, it is s f bar of s minus f of 0, means value of the function at t is equals to 0, and therefore it is s multiplied by s upon s square plus 1 minus value of cos t at 0, t is equals to 0. Cos 0 is 1, and therefore we get s square, s into s, we get s square divided by s square plus 1 and minus 1. And then cross multiplying or finding LCM, we get s square minus in bracket s square plus 1 whole divided by s square plus 1. S square get cancelled, we get minus 1 upon s square plus 1. And you can verify it by taking the derivative of that cos t and then taking its Laplace. We get the same. But here it is expected that we have to apply that Laplace transform of derivative. Therefore, check once again all the steps. And then last example, main use of this Laplace of derivatives to solve the differential equation in inverse Laplace transform. Therefore, I am going to explain one example of that type. Laplace of y double dash plus y is equals to 0, and with initial condition y at 0 is equals to 0 and y dash at 0 is equals to 1. Therefore, it is also called as the initial value problem. Therefore, first step, taking Laplace of y double dash is equals to minus, transferring that y to other side, we get minus Laplace of y. Laplace of second order derivative is s square y bar of s minus sy of 0 and minus y dash of 0, and is equals to minus Laplace of y is y bar of s. Then collecting the terms of y bar of s on one side, means on the left hand side, we get s square plus 1 into y bar of s taking common, and then substituting the value of y of 0 is 0 and y dash of 0 as 1, and then transferring it to right hand side, we get it is equals to 1, and hence we get y bar of s as 1 upon s square plus 1. This is the first part when we are solving linear differential equation by a Laplace transform technique. And in second part we have to take its inverse Laplace, but at this stage I am not explaining that part. When we go for actual study of that inverse, at that time I will explain. Like my video, share it, as well as subscribe to my channel, and to receive the notification of such type of new videos, please press the bell icon. Thank you. Thanks for watching.